Well, let's see if we can look at where we are now. We've done quite a lot. In this video, we're looking at the relationship between electromagnetic waves and transmission lines, and I've set these two columns aside, and here we go. You can see the one-for-one correspondence. It's one-dimensional waves. It's always waves. So let's quickly review T-lines. We wrote the transmission line equations. I don't have to say them. You can read them. The characteristic, intrinsic impedance, square root of L over C. V is equal to 1 over root LC. We did the case for K being complex in general, but most of our work, especially for transmission lines, was done only with the phases. So K was purely real, and we computed the reflection coefficient for the waves when there's a boundary between the line and the load, or between a line of one characteristic impedance and a line with another characteristic impedance. And we also got VSWR and, of course, our dear friend, the Smith chart. EM waves. Well, if you look, E and H equivalent to V and I. We discussed that in the intuitive videos. The forms of the waves, waves traveling to the right, K1 in general is complex. What's different, and we emphasize here in practical situations, is that the intrinsic characteristic impedance for the waves with the symbol eta is mu divided by the effect of epsilon, which can have a real part, and that corresponds to what we have in transmission lines, but it also can have an imaginary part, and that imaginary part is due to the ohmic term in Ampere's law. Furthermore, since the K1 can be alpha plus j beta, it's always going to be true that the phase velocity V is equal to omega over beta. So beta is the imaginary part of K1. Now, really, when we do this, we have to think that it's not just K1, it's actually JK1. So JK1 is this. So JK1 is alpha plus J beta. If alpha is 0, we get J beta Z. So that's what we have.
Very easy to get that wrong.
Yeah, it's very easy to think K1 is this, but it's JK1 is alpha plus J beta.
Mm-hmm.
So we can see all these results are the same, so it doesn't, in a sense, doesn't matter. Just the setting is different. The one thing that is different is the vibration of E and H. We don't talk about that. That we call that vibration. We'll come to talk about it as polarization, and we'll see what its effects are. But basically, we have all the material that we have for one-dimensional electromagnetic wave propagation. And I missed out a few things that are common to both. Sam, what's one of them?
VSWR?
Voltage standing wave ratio, right? But because we're not dealing with voltage anymore, in this case, they'll just call it SWR.
Mm-hmm.
And it has exactly the same definition as it had before. Okay, let's do an example to look at SWR for waves.
Sure. So it's a pretty similar system to what we were looking at yesterday, well, in the other video, where an EM wave is coming into a boundary. On one end, you have a vacuum in material 1, hence alpha 0, lossless. And on the other, you have a conductive, perfect conductor, with sigma being infinite, and you end up with an intrinsic impedance of 0. So if we think about what kind of reflection would happen in this system, if we plug eta 2 into the reflection coefficient equation.
Yeah. Oh yeah, and eta 2 would be 0, yeah. Right? Yeah.
Then eta 2 would be 0, and you're left with negative eta 1 over eta 1, which cancels out to be gamma equals -1.
Now, we've seen that before for transmission lines. So this is a perfect conductor.
Mm-hmm.
And on a perfect conductor, the electric field, which is always tangential to the conductor in this case, because this is the x-axis,
Mhm.
So we have this situation where the reflected wave has a reflection coefficient, gives us the reflected wave of gamma is equal to -1.
Exactly like a short circuit.
That's exactly what I was going to ask you. This works exactly like a short circuit. So let's write down now the expression for the reflected wave. So let's write down the incident wave. So E1 plus.
So E1 plus would be EX phasor form plus naught.
Oh, well, we're going to do this as the amplitude.
Oh, okay.
And then we'll do this X. You want to write that as XS1 there.
Oh, okay.
So there's the phasor 1 X component, amplitude e to the minus j beta z. And now that's that one. Now E minus.
E minus XS1
equals, now slow-mo here. The wave's going backwards.
Yeah. So
and the
positive sign
amplitude
here.
changes. So put that in there.
So multiply this by gamma.
Right.
We get -1 of EX10 plus E plus J beta Z.
All right, so now we're well on our way. What do we have to do next?
Well, if we're looking at, since the wave is fully reflected and we want to look at the standing wave ratio, then we have to add them together and see what relationship that gives, right?
Yeah, let's add the waves together to get the total solution. So that's going to be EXS1 is equal to
this add this, so I'll just do it in one step.
In one step, right.
1, 0 plus 1 minus, wait, no.
No, you don't want 1. You want to
Yeah,
e to the
e
minus
to the
e to the minus j beta z.
E to the negative j beta z minus e to the plus j beta z.
Now I smell Euler here. This looks like a familiar pattern.
You smell Euler?
Yeah, you know, anytime I got this, yeah, it's pretty good. I think you know what the answer is for this one.
Well, I think I do. EX1 naught, if we multiply by 2j, then we can put this sign beta z.
Right. So there's our phasor solution for the total field. Now I want you to write the instantaneous form carefully. We, you know, using the real, so we have to use a script, yeah, E of Z comma T, EX, EX, EX.
Of Z,
it's just an EX1, I guess would be the way to do it. Depending on Z and T equals real. Now, when we do this, I'm going to use this. You're going to have to fit it in here, Sam, right small.
Ooh.
That's going to be hard, but you'll figure it out. We have to take the real part, so we multiply by what?
E to the j omega t.
Yeah, so you got about that much space to write it. Put the e to the j omega t in first, real small. There we go. Now, then put that in.
Sine beta z.
And put a closed bracket there.
Yeah.
All right, so let's do this together. Equals 2x.
Well, so
this is real, this is real.
yes.
And minus, let's just leave the minus in there. So put the 2x naught out. Because
So
it's real,
yeah.
so it doesn't change anything. 2ex naught plus. Now,
Then this breaks into the cos and I sine, well, j sine components. And we know that the cos component will multiply with this J component and actually becoming imaginary.
So we don't count that.
So we don't count the cos component. The sine component carries a J, which would cancel out with this J and produce a -1.
Yep, that's good. So
we
let's
end
write
up
that
with
down.
Sine beta Z and sine omega t. Does that look
And
right?
that's perfect. Now,
Perfect.
so we see that this is a standing wave.
Yes, because there's no translational component.
Yeah, it's not t minus beta over z, it's product. So also, you know where the zeros are. Anytime this is beta z is multiples of pi. And we also know where the peaks are. Peaks are troughs. That's going to be in between, so at quarter wavelengths. And remember that a trough will become a peak at some point because the sign flips between positive and -1, and so a trough can become a peak at a certain time, and it's in the standing wave pattern.
So you just have something
moves.
doing that?
Yeah, and you can see it when a violin string moves. So all the stuff we did about VSWR and standing waves and the locations of max and mins from boundaries, all those things go right over. The math is exactly the same, and we're going to have more exercises related to this, and also maybe 1 or 2 on the Smith charts as applied to EM waves.
Wow, you can apply a Smith chart on EM waves?
Oh yes, we'll do it for the case of no loss, so lossless waves.
That's beautiful.
And it's just fantastic. And just a short note to everyone is that I presented a talk like this in 1995 at California Institute of Technology to the seismologists, and they thought it was really interesting because the Smith chart is a way of summing up infinitely many reflections in a very clever manner.
Wow, that was when I was 1 year old.